Welcome back to Mechanical Engineering Made Simple. Today we cover why pressure vessels don't give a fuck about your calculations. They fail where you stopped looking.
Yeah, it is a harsh metallurgical reality.
Right.
And uh, for anyone standing on a shop floor today, it's really the only reality that matters.
Right. Absolutely. Consider this session like your masterclass. We are setting up the classroom today and speaking directly to you.
Yeah, the people doing the actual work.
Exactly. You, the welder striking the arc, the fabricator rolling the steel, the inspector holding the ultrasonic probe, and the floor engineer signing off on that Hydra test. If you are working with these materials, putting fire to steel, this deep dive is your mission briefing.
Because we are tearing down the hidden mechanics of pressure vessel design here.
We really are, because on a blueprint, a vessel is just this neat, perfectly balanced cylinder of math, but out in the yard, under load, it is a completely different animal.
Oh, totally. We have to start by shifting the fundamental way we, look at these structures. Like, you need to walk up to a pressure vessel, put your hand on the steel, and understand that it inherently contains massive amounts of stored energy.
It's terrifying when you really think about it.
Right. It is essentially a highly engineered, controlled time bomb. The math done in some air-conditioned office might decree that the vessel is perfectly safe.
Sure, on paper.
On paper. But the chemistry of the steel,
Yeah.
the localized thermal gradients, the aggressive operational environment, and most importantly, the microscopic realities of the weld seams.
The stuff you can't see with the naked eye.
Exactly. Those physical elements dictate whether that time bomb remains controlled or whether it finds a microscopic weakness and just exploits it.
A controlled time bomb. I love that. Let's ground that for a second. If you have a vessel holding compressed gas, you aren't just holding air, you are holding the kinetic energy of, billions of molecules desperately trying to expand.
They are constantly pushing.
Constantly pushing against the atomic lattice of the steel. And the primary tool we currently use to contain that violent energy is just math.
Just math.
But when you look at the engineering history and the codes we rely on, it becomes glaringly obvious that the math we use, while legally acceptable and universally applied, is functionally incomplete.
Incomplete is really the operative word there. If we examine the standard governing this entire industry, specifically the ASME code, Section 8, Division 1,
The holy grail for inspectors.
the Holy Grail, yeah.
Yeah.
We are operating under a philosophy called design by rules.
Designed by rules, which, that sounds incredibly authoritative. You follow the rule, you get a safe vessel, right?
Well, it projects authority, but you have to understand its origin. That code philosophy was developed long, long before we had finite element analysis or supercomputers on every desk.
Oh, right. Guys with slide rules.
Exactly. What design by rules actually means is that the code does not require or even expect a detailed evaluation of every single localized stress point in the vessel.
Wait, really? It doesn't require it.
Nope. Instead of calculating exactly what is happening at every microscopic junction, every transition, every weld, the code uses generalized formulas and just applies higher safety factors.
Just bumps up the multiplier.
Right. It essentially operates on the assumption that, hey, we know there are high localized stresses, secondary bending moments, and chaotic forces at play here. But since we can't easily calculate them all by hand, we are just going to bump up the safety factor to cover our blind spots.
Wow. So the industry standard is basically saying, I don't know the exact aerodynamic forces that will hit this specific bridge joint during a hurricane, so I'll just mandate that the whole bridge be built twice as thick.
That's a perfect analogy.
It substitutes a massive blanket of extra steel in place of actual precise knowledge of the stress distribution.
That is the mechanical reality of it, yeah. And the foundational tool used to calculate that blanket of steel is called membrane stress analysis.
Membrane stress, okay.
This is the bedrock for what we call thin-walled vessels. Now, the strict definition of a thin-walled vessel is one where the mean radius of the cylinder divided by the wall thickness is greater than 10.
Mean radius divided by thickness is greater than 10. Okay, so if it hits that ratio, it's officially a thin-walled vessel.
Correct. And in these thin-walled vessels, membrane stress analysis assumes that the state of stress is purely biaxial.
Meaning two directions.
Right. You have longitudinal stress, which is trying to blow the ends of the cylinder off, and you have circumferential or hoop stress, which is trying to split the cylinder straight down the middle.
Got it. What about the pressure pushing outward against the wall itself?
That's the radial stress. And the math actually considers it so small compared to the hoop and longitudinal stresses that it simply ignores it.
It just ignores it completely.
Completely.
Yeah.
Furthermore, and this is the really critical part, this analysis assumes that these tension or compression stresses are completely uniform across the entire thickness of the vessel wall.
Uniform across the entire wall. Okay, let's unpack the physics of that assumption for a second.
Yep.
Is membrane stress basically treating the steel like the skin of a balloon?
Yeah, that's exactly the mindset.
Because when you blow up a rubber balloon, the rubber stretches uniformly, right? The math assumes the inside of the rubber skin is handling the exact same amount of pressure as the outside of the rubber skin. It's a perfect uniform membrane.
In a perfect world, sure.
But here is the massive disconnect from the shop floor. I mean, industrial pressure vessels are not party balloons. They don't exist in a perfect vacuum. You have heavy, multi-ton steel nozzles welded into the side of them.
Oh, yeah.
You have wind shears pushing them laterally. You have seismic loads, extreme thermal gradients where one side of the vessel is freezing cold and the other is subjected to boiling fluids.
You are hitting on the exact catastrophic limitation of the membrane assumption right there.
Uh-huh.
In a vessel of complicated shape, which is honestly almost every vessel in actual industrial service, simple membrane stress concepts completely fail to describe reality.
Because reality is messy.
Right. The deviations from that perfect mathematical balloon shape dictate the true stress. The heavy heads closing off the ends of the vessel, the variations in plate thickness, the heavy nozzles you mentioned.
The support lugs.
Yes, external support lugs, or even the bending caused by a strong wind. All of these set up severe bending moments in the vessel wall. The direct internal pressure loading is diverted from the flexible, thin parts of the shell to the more rigid, heavily welded parts.
So the force actually shifts.
Exactly. This forced diversion of force introduces what we call discontinuity stresses.
Discontinuity stresses. So these are the areas where the math breaks down and the physical chaos takes over.
Yeah, they are highly localized, intense stress concentrations that occur anywhere two different geometries meet. Like, think about where a thin cylindrical shell meets a thick, heavy forged nozzle.
Or where the shell terminates into one of those huge hemispherical heads.
Exactly. When the vessel pressurizes, the thin shell wants to expand outward like your balloon. But the thick nozzle, or the rigid head, it refuses to expand at the same rate.
It's too stiff.
Right. So the structure has to violently deflect, bend, and rotate together just to stay physically connected. That forced compatibility, two pieces of steel fighting over how much to expand, creates massive localized stress that the basic membrane formula just completely ignores.
Man. And the plot thickens even more when we step away from the balloon entirely and look at thick-walled vessels, right? When that mean radius divided by the thickness is less than 10, that radial stress we were so happily ignoring suddenly demands a seat at the table.
Oh, it becomes the dominant factor. In a thick-walled vessel subjected to extreme internal pressure, like think of high-pressure chemical reactors or deep-sea submersibles.
The stuff that has to survive crazy conditions.
Yeah, the uniform stress equations are just thrown out the window. The stress is no longer uniform across the wall.
Yeah.
The maximum circumferential hoop stress and the maximum radial stress both occur heavily concentrated on the absolute inside surface of the cylinder wall.
So the inside fibers of the steel, the actual atomic layers physically touching the pressurized fluid, are taking a brutal beating.
A massive beating.
They are experiencing maximum stress and essentially screaming under the load, while the outside layers of the steel are barely registering the pressure at all.
That is the mechanical state, yes. But here is the paradox that makes thick-walled vessel engineering so fascinating. Failure of the shell does not begin at the bore. The inside yields, but the vessel does not fail from the inside.
Wait, hold on. If the inner layers of steel have yielded, like if they've reached their elastic limit and permanently deformed under the pressure, how is the vessel still holding together?
It sounds impossible, right?
Yeah. Why doesn't a crack just instantly open up and propagate to the outside? I mean, how can yielded steel hold back a bomb?
Because those inner fibers, while yielding, are physically trapped. They are entirely surrounded and restricted by the massive outer portions of the steel shell.
Oh, they have nowhere to go.
Exactly. The inner steel reaches its yield point, but it has nowhere to expand into. So the metal engages in a phenomenon called plastic flow. The inner layers essentially say, well, I cannot absorb any more of this force elastically without tearing. So they permanently deform just enough to transfer that excess load radially outward to the next unyielded layer of steel.
That is wild. They literally pass the buck to the next layer of molecules.
They do.
Yeah.
This forces the circumferential stress to artificially reduce at the inner layers and dramatically increase at the outer layers. The load keeps moving outward layer by layer until the absolute outside of the cylinder reaches maximum hoop stress.
Wow.
Therefore, the eventual catastrophic failure initiates at the outer surface, tearing inward, even though the inner surface yielded first.
That is a phenomenal survival mechanism. The inner steel yields, but the outer steel acts like an unyielding cage, absorbing the transferred load until the cage itself finally breaks.
It is an incredible property of ductile metals. It's a phenomenon entirely reliant on stress redistribution. And we actually weaponize this behavior in advanced manufacturing techniques like autofrettage.
Autofrettage, what's that?
So in autofrettage, we take a thick-walled forged cylinder like a cannon barrel or a hypo-pressure pump, and we intentionally, vastly overpressurize it during testing.
You break it on purpose.
We force the inner layers to yield and plastically deform, yeah. When we release the pressure, the outer layers try to spur back to their original shape, but the inner layers are now permanently larger.
Oh, so they're fighting each other.
Exactly. This creates a massive, permanent compressive stress on the inner bore, essentially armoring it against future internal pressure. But it proves the ultimate point, right? The baseline math assumes a uniform wall, but the material's physical, atomic reality dictates how it actually behaves, yields, and survives under extreme duress.
So, since our standard rulebook math and our baseline membrane assumptions essentially gloss over these local stresses, bending moments, and complex load-sharing behaviors, what actually happens when those ignored localized stresses finally exploit a weakness in the material?
Things go boom.
Yeah, we need to step off the chalkboard and look at the actual wreckage. We need a practical autopsy of failure.
We absolutely need to look at how vessels die. In industrial failure analysis, vessel failures generally fall into four major categories. You have material, design, fabrication, and service. Every single rupture, leak, or explosion has a distinct how and why tied to those four pillars.
Okay, let's dig into a specific autopsy then. There is a documented failure of a boiler drum that perfectly illustrates what happens when service conditions exploit a design discontinuity. Walk us through the physical mechanics of this failure.
Okay, to understand this, you have to picture the service environment of a heavy industrial boiler drum. We are talking about a massive steel cylinder operating at incredibly high temperatures and pressures, filled with boiling water and saturated steam.
Like, the steel itself is practically glowing.
Exactly. Now, to keep this boiler generating steam, you have to constantly introduce fresh water into it. That feed water is injected through a specific nozzle, and that feed water, by necessity, is significantly cooler than the operating temperature of the drum itself.
So you have a constant stream of cool water directly impacting the immensely hot steel at a specific geometric discontinuity, that inlet nozzle junction.
Right. And consider the thermal physics of that interaction. Every time that cooler water hits the hot steel surrounding the nozzle, it causes a sudden, highly localized drop in the surface temperature of the metal.
And metal shrinks when it gets cold.
It contracts, exactly. The steel right at the nozzle tries to shrink, but it is physically restrained by the massive, still hot, fully expanded drum surrounding it. The hot drum refuses to let the cooling steel shrink.
Oh, man.
This creates a severe, microscopic tearing force known as a thermal stress.
It's essentially the metal trying to pull itself apart just because of the temperature differential.
Yes. Now, thermal stresses are technically classified as secondary stresses in engineering mechanics. They are considered self-limiting, meaning once the local part yields just a little bit or the temperature equalizes, the stress relaxes. A single thermal shock of this magnitude usually won't rupture a thick piece of ductile boiler steel. It will just stretch it slightly.
But a boiler isn't a single shock environment. It's a continuous operating power plant. This injection of cold water is happening repeatedly.
And that introduces the silent killer, which is fatigue. Fatigue is a strictly cycle-dependent phenomenon. You are subjecting that specific nozzle junction, which, remember, is already suffering from high discontinuity stresses just from its awkward non-membrane shape.
Right, because it's a nozzle on a cylinder.
Exactly. You are subjecting it to an endless rhythmic cycle of violent thermal contraction and expansion.
Okay, let's unpack this. If I'm the floor operator monitoring this boiler, I'm looking at my pressure gauges and everything is deep in the green. The pressure isn't exceeding the ASME design limit. The safety valves aren't lifting.
The math looks perfect.
The standard math says the vessel is perfectly safe. But the math can't see the microscopic expansion and contraction happening at that nozzle. It is literally like taking a heavy-duty steel paperclip and bending it back and forth, back and forth. I'm not pulling the paperclip apart with sheer tensile force. I am just cycling it until the molecular bonds give up.
That paperclip analogy is the exact mechanical reality of fatigue. The damage is accumulating on a microscopic level during each thermal cycle. What happens is that the continuous push and pull causes microscopic slip bands to form in the crystalline structure of the steel.
Which turn into cracks.
Eventually, yes, these slip bands develop into microscopic cracks. With every subsequent injection of cold water, the stress concentrates at the razor-sharp tip of that tiny crack, prying it a few atoms deeper.
And it just keeps sticking.
The cracks grow, they join together, and they spread through the wall thickness. Progressive fracture develops. In failure analysis, it's incredibly common to see the actual design strength of a component cut by 50%, simply due to poor design details at these thermal junctions.
Wow. 50%.
Yeah, the overall internal pressure doesn't even need to be anywhere near the static elastic limit of the seal. The boiler drum fails, it blows out at the nozzle, not from overpressure, but from localized thermal exhaustion.
It just gets tired and lets go. That is a brutal blind spot. Now, let's look at another failure scenario. Fatigue takes months or years to kill a vessel. But there is another mechanism that destroys vessels instantly. A brittle fracture during a routine hydro test.
Oh, these are terrifying.
Let's set the scene for you. The vessel is perfectly calculated. The math is flawless. It's constructed of standard, code-approved low-carbon steel. The fabricators roll it out into the yard for its final proving test, and they fill it with water. The ambient temperature of the water happens to be between 40 and 50 degrees Fahrenheit.
Which, to a human, is just a brisk autumn day. It doesn't sound like an extreme cryogenic environment at all.
It sounds completely benign. But hidden deep inside one of the longitudinal welds is a microscopic, completely unnoticed flaw, a tiny slag inclusion, or a lack of fusion. The inspector missed it, the pumps turn on, the internal pressure goes up to test pressure, and suddenly, catastrophically, the massive steel vessel just shatters.
It doesn't yield at all.
It doesn't stretch, it doesn't bulge or leak, it explodes like a dropped pane of glass. What is the physical mechanism behind this?
This failure is entirely dictated by the intersection of material properties and thermodynamics. We are dealing with brittle fracture. To understand this, you have to look at the crystalline structure of standard carbon steels. They possess what metallurgists call a ductile to brittle transition temperature.
A temperature threshold that literally changes the physical nature of the metal.
Exactly. Above a certain temperature, the steel is ductile. Its atomic lattice has the ability to slip and slide when subjected to force. If you overload a ductile vessel, it will physically stretch, bulge like a tire, and eventually tear open relatively slowly. This plastic deformation requires a massive amount of energy, which means the material absorbs the explosive force before failing.
Which is the entire goal of mechanical design, right? We want a structure to groan, bend, and give us a warning before it fails.
A warning is what saves lives. But if the temperature of the steel drops below that critical transition point, the molecular behavior fundamentally shifts. The atomic slip planes lock up. The steel loses its ability to deform plastically. It essentially becomes glass.
Unbelievable.
Now combine that chilled steel, sitting at 45 degrees Fahrenheit, with a microscopic sharp flaw in a weld.
That flaw is no longer just a void, it becomes a force multiplier.
It acts as an infinite stress riser. When the hydrostatic pressure builds, all the force is intensely concentrated at the microscopic tip of that hidden crack. In ductile steel, the metal at the crack tip would just stretch and blunt the crack, safely absorbing the stress.
But because it's cold.
Because the steel is below its transition temperature, it cannot yield. It cannot blunt the crack. The stress exceeds the cohesive atomic strength of the metal, and the crack propagates. And because there is no plastic deformation to slow it down, a brittle crack travels through the steel at acoustic velocities.
Wait, acoustic velocities?
Literally the speed of sound through metal. The vessel unzips and shatters instantly, with zero warning.
That's a catastrophic blind spot. You could have an engineer standing 3 feet away with a clipboard, verifying the pressure gauges, thinking everything is perfectly fine because the water is only 40 degrees and the vessel just detonates.
It highlights exactly why the material category of failure analysis is so critical. The designer blindly selected a standard low-carbon steel without adequately analyzing the thermodynamics of the intended hydrotest conditions. The material was structurally sound for a warm operating environment, but it was a ticking bomb at 40 degrees.
So we have fatigue, which wears the metal out through rhythmic thermal or mechanical cycles like the boiler drum. We have brittle fracture, which shatters cold metal instantly from a microscopic flaw. But there is a third major mechanical failure mode that operates on an entirely different timeline. Creep.
Creep.
What is the physical difference between creep and fatigue?
Creep is an entirely different metallurgical phenomenon. While fatigue is driven by cycles, expanding and contracting. Creep is a time-dependent deformation. It is the silent stretching of metal.
The silent stretching.
Creep occurs when a material is subjected to high constant stress while sitting at highly elevated temperatures, usually in the red-hot ranges of a superheater tube or a high-temp catalytic reactor.
So the load isn't cycling, it's just a constant, heavy push in a very hot environment.
Right. Over time, even if the internal pressure never spikes and the temperature remains perfectly stable, the material will slowly, continuously deform. At those elevated temperatures, the thermal energy allows the atoms within the metal lattice to slowly migrate. The microscopic grain boundaries of the steel actually begin to slide past one another. The material literally flows like an incredibly viscous fluid.
It's just slowly stretching itself to death over thousands of hours. The engineering postmortems refer to this as a fish mouth rupture, right?
That describes the physical geometry of the failure perfectly. As the tube or vessel wall slowly creeps, it begins to bulge outward, and the wall thickness gradually thins down, much like stretching a piece of warm taffy.
Getting thinner and thinner.
Eventually, after thousands of hours in service, the wall becomes so thin that it can no longer contain the baseline operating pressure. It bursts open in a wide, gaping longitudinal split. The edges of the rupture are razor thin because the material is just stretched away. It looks exactly like the open mouth of a fish.
Wow.
So you have fatigue, wearing the molecular bonds out through repetition, creep stretching the grain boundaries to death over time at high heat, and brittle fracture shattering the lattice instantly in the cold.
Which brings us to the ultimate engineering pivot. If we know that cyclic loads, freezing hydro tests, and high-temperature creep can so easily destroy standard carbon steel, the obvious question for an engineer is, well, what metal do we use to stop this?
We have to change the chemistry.
Exactly. How do we build a vessel that actually survives these environments?
This is where advanced metallurgy takes the stage. When we are designing for environments that are actively, chemically, trying to destroy the vessel, specifically in the chemical process, petrochemical or desalination industries, where you are dealing with concentrated chlorides or highly acidic agents,
The really nasty stuff.
standard carbon steel, or even your basic 300 series stainless steels simply will not survive. They will be eaten alive by localized corrosion.
The evolution in materials is fascinating here. We aren't just talking about adding a little more nickel. The industry has moved toward complex microstructures, specifically dual-phase stainless alloys, metals like beryllium-255 and alloy 2205.
Game changers, honestly.
What physically makes an alloy dual-phase, and why does it matter?
To understand dual phase, or duplex stainless steels, we have to look through a microscope at how the metal crystallizes when it solidifies. Most common stainless steels, like the 316 you might have in your kitchen sink, are entirely austenitic in their crystal structure.
Austenite, okay.
Other types, like the steel used in automotive exhaust, are ferritic. Both have massive strengths and massive weaknesses. Austenitic is incredibly ductile and weldable, but vulnerable to chloride stress corrosion cracking. Ferritic is highly resistant to cracking, but can be brittle and difficult to weld.
So you have two distinct crystalline families, and each has a fatal flaw.
Exactly. So metallurgists asked, what if we carefully control the chemistry, specifically the precise ratios of chromium, molybdenum, nickel, and nitrogen, and create an alloy that solidifies as a 50-50 mix of both crystalline structures?
It's a hybrid.
Yes. They force the metal to form an alternating microscopic lattice of austenite and ferrite grains. By combining the two phases, the alloy miraculously adopts the best properties of both.
And the performance data on these duplex alloys is staggering. The engineering data states that these dual-phase alloys possess yield strengths that are roughly 30% stronger than standard 316 stainless steel.
It's a huge leap.
You get a massive bump in physical strength, alongside an incredible resistance to localized pitting and crevice corrosion in chloride environments.
The strength-to-weight ratio is a game changer. That high chromium and molybdenum content locked in that dual-phase microstructure makes them incredibly resilient against chloride ions, which are notorious for drilling microscopic holes straight through standard stainless steel. But as with everything in structural engineering, there is no free lunch.
There never is.
There is a serious fabrication catch.
Right, there is always a tax to pay on the shop floor. What happens when the welder gets their hands on it?
The tax is paid in ductility and workability. Because duplex stainless steels are so much stronger and harder, they have significantly less ductility than standard austenitic stainless. They resist deformation.
They fight back.
They do. This means they require extreme surgical care in both cold forming and welding. If a fabricator tries to roll a heavy duplex plate through the bending machine using the same parameters they use for carbon steel, or if a welder pumps too much heat into the joint and cools it improperly, they will destroy the delicate 50-50 microstructural balance.
They ruin the magic ratio.
Exactly.
Huh.
They will introduce microscopic cracks, precipitate out brittle intermetallic phases, and completely ruin the corrosion resistance that the client just paid a massive premium for.
So you need an absolute master fabricator. Now, how do design engineers actually measure or predict how well one of these premium alloys will survive a specific chemical attack? You can't just guess that the metal will hold up. There has to be a predictive mathematical model.
There is a very specific metallurgical tool for this. It is called the pitting index, often referred to as the PREN, or pitting resistance equivalent number.
QIRN, got it.
This is a crucial calculation for predicting a metal's survival in aggressive, chloride-heavy environments. The equation is straightforward, but the variables dictate the life of the vessel. Pi equals the percentage of chromium plus 3.3 multiplied by the percentage of molybdenum plus X multiplied by the percentage of nickel.
I want the engineers listening to visualize that formula. Pi equals the percentage of chromium plus 3.3 multiplied by the percentage of molybdenum plus X multiplied by the percentage of nickel. Let's break down the chemistry of that math. Chromium builds the invisible oxide layer that makes stainless steel stainless. Molybdenum reinforces that layer against aggressive chlorides. But explain that X factor, because that seems to be the variable that shifts depending on the crystal structure.
The X factor is the structural modifier. It changes entirely depending on the microstructural family of the steel you are analyzing. If you're calculating the index for a purely ferritic stainless steel, X is 0. The nickel content doesn't heavily influence the pitting resistance.
Okay, 0 for ferritic.
But if you shift to a duplex stainless steel, our dual-phase alloys, the X factor jumps to 16. And if you are evaluating a fully austenitic stainless steel, X goes all the way up to 30. By calculating this index, engineers can evaluate the process fluid, say a mixture with a specific part per million of chlorides and a high pH, and set a strict minimum pitting index required for the steel to survive satisfactory operation at high temperatures.
Here's where it gets really interesting, because even with the perfect pitting index, there is a nightmare scenario that combines two failure modes we've already discussed. We talked about mechanical fatigue tearing metal apart, and we just talked about chemical corrosion eating it away. But in the real world, these forces combine into a devastating hybrid: corrosion fatigue.
It's the worst of both worlds.
The structural engineering models call it a co-joint mechanism. How does this electrochemical feedback loop actually work?
It is arguably the most deadly feedback loop in mechanical engineering, and it has caused catastrophic failures in massive infrastructure. Think about how the two mechanisms operate independently. Corrosion alone works on a slow timescale, gradually eating away the surface. Fatigue alone works on a cycle scale, slowly initiating micro cracks over millions of bends.
But when they team up,
Right. When you subject a part to cyclic stress while it is immersed in a corrosive fluid, the effects are not merely additive, they are intensely multiplicative. The damage is worse than both actions taken separately or sequentially.
walk us through the electrochemistry of it. Put us inside a chemical process tank. Say we have a massive rotating mixer shaft blending a heavy corrosive slurry.
Okay, you have this heavy stainless steel mixer shaft. Because it is rotating through a viscous fluid, it is under constant heavy cyclic bending stress. As the shaft rotates, the surface fibers of the steel go into tension, then compression, then tension again. Now the shaft is submerged in an aqueous, highly corrosive environment. Here is where the physics gets dangerous. On an atomic level, metals actually become more anodic in localized areas of high tensile stress.
Anodic meaning they actively give up electrons. They become a massive glowing target for a chemical attack.
Precisely. The chemical fluid acts as an electrolyte and aggressively attacks that highly stressed anodic band on the shaft. It strips away the protective oxide layer and creates a microscopic pit. Now, from a mechanical standpoint, that pit represents a sudden change in the surface geometry of the smooth shaft. The pit immediately acts as a stress riser.
It's a flaw.
Yes, it becomes a microscopic focal point that drastically concentrates the mechanical bending stress.
So the mechanical stress chemically created the pit, and now the pit is mechanically multiplying the stress.
Exactly. It is a vicious, accelerating cycle. The intensified, multiplied stress at the bottom of the microscopic pit worsens the fatigue damage, physically tearing the lattice and creating a microscopic, sharp crack at the root of the pit. As the crack opens during the tension cycle, it exposes fresh, unoxidized, highly stressed steel, to the corrosive fluid.
And the fluid just rushes right in.
The fluid rushes in and rapidly corrodes the crack even deeper. The crack deepens, which further concentrates the mechanical stress, which tears the crack further, which invites more corrosion. The shaft will shear completely in half in a fraction of the time, and at a fraction of the stress level you would expect from fatigue or corrosion acting alone.
That is horrifying. The environment and the mechanical load are actively conspiring to drill a hole through the metal, which proves exactly why picking the right alloy and getting that pitting index right is a matter of life and death.
Without a doubt.
But that transitions us to the most vulnerable part of the entire vessel. Because even if the lead engineer picks the absolute perfect dual-phase alloy and they calculate the pitting index flawlessly and they account for corrosion fatigue, it means absolutely nothing if the welder on the floor doesn't join the massive plates of metal correctly.
The individual holding the welding torch holds the integrity of the entire engineering team's design in their hands. We can debate allowable stress formulas and pitting indexes all day in the conference room, but a pressure vessel is, fundamentally, only as strong as its weakest welded joint.
Let's talk about how the engineering codes actually account for the human element of welding. They use a critical multiplier called joint efficiency, represented in the formulas by the Greek letter eta.
Joint efficiency is the code's mathematical translation of our confidence in the physical weld. It is a harsh, unforgiving multiplier. A perfect, flawless weld, fully fused with the parent metal, has an efficiency of 100%, or 1.0.
But you don't just get that 1.0 for free.
Oh, absolutely not. The code does not grant that 1.0 efficiency based on the welder's reputation or how pretty the weld cap looks. We only grant an efficiency of 1 if we have proven it through full, volumetric, non-destructive testing, specifically full radiographic testing.
X-rays.
That means we have X-rayed the entire length of the weld seam and visually confirmed there are no hidden voids, no trapped slag inclusions, and no subsurface cracks.
But X-raying every single inch of a multi-ton vessel is incredibly expensive and time-consuming. So a lot of vessels are designed without full radiography. What happens to the math if the weld isn't X-rayed?
The code aggressively punishes you. If a longitudinal butt weld is left entirely non-radiographed, the code automatically assumes there are hidden flaws inside of it and drops its efficiency to 70% or 0.7.
That is a 30% penalty right off the top. How does that translate to the physical steel and the overall safety factor of the vessel?
It creates a massive shift in the vessel's construction. Think about the safety factors. If you pay for the radiography and prove the longitudinal butt weld has an efficiency of 1, the standard ASME code applies a baseline factor of safety of 4 against the ultimate tensile strength of the steel. You are dividing the failure pressure by 4 to find your safe operating limit.
Okay, factor of 4.
But if you choose the non-radiographed route with an efficiency of 0.7, your effective factor of safety mathematically jumps from 4 to 5.7.
Which means the math is forcing you to make the steel of the vessel dramatically thicker, much heavier, and vastly more expensive to procure and ship, simply because you chose not to look inside the weld to prove its integrity.
It is a literal ignorance penalty paid in raw steel. And the physical thermal mechanics of the welding process explain exactly why the code demands that penalty. We have to consider the heat-affected zone, or the HAZ.
The HAZ, let's get into that.
When a welder strikes an arc to melt the steel, they are pumping thousands of degrees of localized thermal energy into the joint. But that heat doesn't stay in the weld pool. It conducts rapidly into the solid parent metal, immediately adjacent to the weld.
And that heat wave alters the molecular destiny of the steel.
Profoundly. It completely changes the microstructure of the steel in that boundary zone. Depending on the cooling rate, the heat-affected zone can undergo excessive grain growth, making it wet. Or if it cools too fast, it can form brittle microstructures like martensite, making it highly susceptible to cracking. In stainless steels, improper heat input can cause chromium carbides to precipitate at the grain boundaries, literally stripping the steel of its corrosion resistance right next to the weld. The HAZ is a metallurgical minefield.
And beyond the microscopic changes, there is the massive physical importance of alignment. When you are rolling massive plates of steel into a cylinder and fitting them up for welding, it is incredibly difficult to get them perfectly flush. But why is it so mechanically critical that the two plates line up flawlessly?
It comes down to how the invisible lines of force flow through the metal under pressure. Imagine the tension running straight through a uniform piece of steel plate. Now, if two plates are welded together but are slightly misaligned, offset by just a fraction of an inch, The force trying to pull them apart cannot flow in a straight uniform line.
It has to bend.
The force has to physically jog around the corner of the misalignment to continue through the vessel. This sudden detour creates a severe bending moment directly at the root of the weld. It introduces massive localized bending stresses that the baseline membrane formulas simply do not account for. To prevent this from tearing the weld apart, the code sets incredibly strict alignment tolerance rules.
How strict are we talking for a critical seam?
For longitudinal seam, which is the most highly stressed joint on the vessel, the maximum allowable misalignment is strictly governed by the thickness of the plate. The absolute maximum offset is the plate thickness divided by 10, and even then, it is hard capped at a maximum of only 5 millimeters, regardless of how thick the steel gets.
Plate thickness divided by 10. On a half-inch thick vessel, that is practically zero margin for error. A fraction of an inch of offset, and the inspector flags it. Now, you mentioned the longitudinal seam being the most highly stressed joint. Let's dig into the physics of that. We have the longitudinal seam running the length of the cylinder and the circumferential seam wrapping around the belly of it. Why is the longitudinal seam so much more critical?
This goes back to the foundational physics of a pressurized cylinder. When internal pressure pushes outward against the wall, it creates two primary stresses. Hoop stress, which is trying to split the cylinder lengthwise like a hot dog on a grill, and longitudinal stress, which is trying to blow the end caps off the cylinder. Because of the geometry of a cylinder, the hoop stress is always, mathematically, exactly twice the magnitude of the longitudinal stress.
So there is twice as much force trying to split the vessel down the middle as there is trying to stretch it end to end.
Correct. Therefore, the longitudinal weld, the seam that physically holds the cylinder together against that splitting force, is fighting a battle twice as hard as the circumferential weld. The longitudinal seam is the ultimate weak link. It is the most critical pressure boundary in the entire design.
Okay, I have a practical pushback here. Put me in the boots of the fabricator. I just laid down a massive weld on a critical discontinuity joint, maybe where a heavy nozzle meets the shell. I met my strict alignment tolerances. But my weld cap, the visible top of the weld, it looks rough. It's fully fused, but it's a bit convex, maybe a little lumpy. I know the client wants a pretty vessel. Can I just take a heavy angle grinder to it? Can't I just grind the weld cap down perfectly flush with the base metal to make it look smooth and professional?
Metallurgically and structurally, that is a terrible idea, and any seasoned inspector will shut you down immediately. Excessive grinding is totally unacceptable and deeply dangerous. When a fabricator takes a grinder to a weld just to make it look visually pleasing, they run an incredibly high risk of inadvertently cutting into the parent metal immediately adjacent to the weld toe.
You are accidentally thinning the actual pressure boundary of the vessel.
Yes, you are creating what is effectively an artificial undercut, and it is exceptionally dangerous at those critical discontinuity joints. Remember earlier when we discussed the chaotic discontinuity stresses at nozzles and head-to-shell junctions?
Right, where the forces are already going crazy.
Those specific junctions are already experiencing massive, complex bending stresses, just trying to hold the dissimilar shapes together under pressure. If you go in there with an aggressive grinding wheel and thin the wall of the parent metal, you are literally removing the exact load-bearing steel that is desperately needed to fight those bending stresses. You are taking the most stressed point of the vessel and making it physically thinner. You are handcrafting a failure point.
You are trading structural integrity for aesthetics, which is a lethal trade, which perfectly sets up the final phase of a vessel's creation. The welder did their best. They aligned the plates perfectly. They didn't overgrind the cap. The metal is cooled. How do we actually prove this multi-ton steel bomb won't explode when we put it into service? We test it. But when you look closely at industrial testing protocols, there is a very dark truth about what these tests actually prove.
It is a truth that makes a lot of people in the industry deeply uncomfortable. The universal final standard for vessel acceptance is the hydrostatic test. The vessel is hauled into the yard, filled entirely with water, and pressurized to usually 1.25 or 1.5 times its maximum allowable working pressure.
It's the ultimate stress test. And if, for some process reason, you absolutely cannot introduce water into the vessel, the codes allow for pneumatic testing using compressed air or nitrogen. But from a physics standpoint, that sounds incredibly dangerous.
Pneumatic testing is terrifying. It demands the utmost respect and extreme safety protocols. Because gases compress, they act like a massive coiled spring. They store an immense amount of potential kinetic energy. Think about the difference. If a vessel contains a microscopic flaw and fails during a water hydro test, it usually just splits open and aggressively leaks.
Because water doesn't compress much.
Right? Water is virtually incompressible. The moment the steel breaches, the internal volume barely expands and the pressure drops to zero almost instantly. But if a vessel fails during a high-pressure pneumatic test, that compressed gas violently expands to its atmospheric volume. It turns the vessel into a literal fragmentation bomb. The energy release is astronomical. This is why safety regulations strictly mandate that high-pressure pneumatic tests must be conducted with the vessel completely evacuated of personnel, placed in a reinforced pit, or entirely surrounded by heavy concrete blast walls.
That paints a vivid picture of the stakes, but whether you are using water or using a gas, the core issue is what the test is actually verifying. What does a successful pressure test functionally prove?
The harsh reality is this. A pressure test is a test for macroscopic leakage and gross yielding under temporary static pressure, and that is about all it is.
Wait, it's just a leak test. People treat a hydro test signature like it's a blessing from the engineering gods. If a vessel passes hydro, the general consensus on the floor is that the vessel is invincible.
That assumption is the proving fallacy, and it has caused countless disasters. Pumping a steel vessel full of water and holding it at pressure for 30 minutes at room temperature does not prove the vessel will resist cyclic thermal fatigue over 10 years of operation.
Like the boiler drum.
Right. It does not prove the alloy will resist high-temperature microstructural creep. It does not prove the dual-phase steel won't fall victim to stress corrosion cracking in a hot chloride environment. And most importantly, the hydro test is not a reliable proving test for detecting hidden internal weld defects that simply haven't propagated all the way to the surface yet. A slag inclusion sitting in the dead center of a thick weld will pass a hydro test today, and it will tear the vessel apart 5 years from now.
So what does this all mean? If I'm the floor engineer signing my name on the final acceptance documentation and I know the hydro test only proves the vessel doesn't leak today, how do I know it's truly safe for tomorrow? What is the actual safety net?
It means you have to recognize the hydro test as merely the final rudimentary checkbox. The true lifesavers, the sophisticated tools that actually guarantee the long-term integrity of the vessel, are the non-destructive testing methods. These are the tools that look beyond the surface. Visual examination by a trained inspector to catch dangerous undercuts, poor weld profiles, and misalignment. Radiographic testing, the RT, where we use heavy isotopes to shoot X-rays straight through the solid steel and expose the hidden volumetric voids and slag on film. And ultrasonic testing, UT, where we bounce high-frequency sound waves deep through the atomic lattice of the metal to detect microscopic planar cracks that X-rays might miss. If a shop skimps on the NDT, their successful hydro test is nothing but a false sense of security.
That is a deeply sobering thought to anchor our discussion. It brings everything we've talked about full circle. We started with the illusion that mathematical formulas provide perfect safety, and we ended with the illusion that a simple pressure test guarantees a perfect vessel. The reality, the true line between safety and catastrophe always lies buried in the physical, microscopic details. The dual-phase chemistry of the alloy, the thermal control of the welder, and the uncompromising honesty of the ultrasonic inspector.
That is the ultimate takeaway. And it actually brings me to a final, somewhat philosophical point regarding the physics of metals. It builds directly on the mechanics of plastic flow and stress redistribution that we unpacked when discussing thick-walled vessels.
I love when the physics gets philosophical. Let's hear it.
We spent significant time detailing how, in a highly pressurized, thick-walled cylinder, the innermost fibers of the steel reach their breaking point first. They yield, but they don't fracture. They engage in plastic flow. They physically alter their atomic arrangement to transfer their immense load to the neighboring unyielded fibers further out in the wall. Think deeply about the mechanical implication of that. Ductile metals have an inherent built-in survival instinct. When a highly localized point gets overstressed, the metal actually sacrifices its original shape.
It yields and stretches.
Exactly. It yields and stretches to violently force its neighboring molecules to help carry the burden. The entire vessel actively tries to save itself, desperately attempting to share the localized stress across its entire macrostructure before it ever initiates a fatal rupture.
The atomic lattice actively wants to survive. It literally deforms itself to share the load.
It does. And the question that should linger in the mind of every mechanical engineer detailing a blueprint, every fabricator rolling a plate, and every welder striking an arc is this. Are you designing and building systems that allow the material to flex and share its burden naturally? Or are your rigid designs, sharp transitions, and heavy welds restricting the metal so severely that its only possible option is to break?
That is a phenomenal question to leave them with. Waste is inevitable. Perfection is a fantasy. Build anyway. Fail forward. Thanks for listening, and don't forget, If this helped you even a little, please tell us. We're putting this out for free, no paywall, no subscription, nothing locked behind a card. That only works if we know it's actually reaching and teaching. If this gave you clarity you weren't getting anywhere else, drop a like, leave a comment. It takes 2 seconds on your end, but it tells us this is worth continuing.